Thank you very much for the introduction, but also for the very kind invitation. That's a great pleasure to share my work done in Strasbourg by my group on let's say an approach that we have from the molecular side on the two-dimensional materials. And so we are chemists, but you will see that we actually try also to invade other territories, like the one of device fabrication. And so the whole community, I think the whole science has been facing the graphene revolution over the last 20 years or so. So there's been a big hype. Well, whether it is a hype or not, we will probably need a few years more. But this really opened our eyes and made our dream become say more and more intense towards looking for a technological solution using this kind of ultralight materials with unique properties. So graphene is just the first one. Today, indeed, I will speak very little about graphene, and we will move to other type of two-dimensional material. But graphene exfoliation and outstanding physical property has been unraveled by the two colleagues in Manchester, Andre Gaim and Kostya Novoselov, really opened the door to a new potential technology in different touching different type of application. You see automotive sensing, security, touch screen, digital contact lens, communication, electronics, renewables, and so on and so forth. Now, of course, graphene was the first of a wide portfolio of two-dimensional materials. So this kind of two-dimensional material, they look different, so they can appear in different colors, but they share a number of properties, like, for example, the diversity of the atomic composition, atomic thickness, flat surface, large surface to volume ratio, excellent physical and chemical properties. Environment, and that is a characteristic I will use mostly during my presentation of today. So presently, theoreticians, which are always extremely optimistic, they claim that one can exfoliate up to 3,000 different type of layered materials into two-dimensional nanosheets. Now, of course, as I said, experimentally is always much slower. And at the moment, there are about 100 different types of two-dimensional material that have been exfoliated and are under study. Now, within this kind of library of 100 different types of two-dimensional materials, there is already the possibility to span from, let's say, materials with totally different electronic properties. It goes from insulator, like boron nitride, all the way down to superconductor, that's the one of niobium diselenide. And in between, you have a semiconductor, half metal, semi-metal, and metals. Okay, we will focus today mostly on semiconductors, and that are in particular transitional metal dichalcogenides. Now, if I look from the chemistry perspective, the characteristics of two-dimensional materials, I can claim that they have outstanding physical properties like mechanical, electrical, optical, and so on. But actually, they have a weakness that their properties are hardly tunable. And this is where the molecular approach comes into the game. And our view and our strategy in my group is the one of combining two-dimensional material with molecular science as a way to tune and improve the physical properties of two-dimensional materials, and also as a way to impart a new property to two-dimensional materials. And this is a way to make them multifunctional. Now, how do you combine these two worlds, the world of molecular science and the world of two-dimensional materials? Actually, you can use very well-established interaction type that have been used to study matter and interface. For example, you can use very weak interaction like van der Waals forces that you have on the extreme left, or all the way down to the most strong forces you can think of that are covalent functionalizations. And so in between, you have dipole-dipole interaction, you have charge transfer, and defect healing. Now, in this cartoon, from the center to the left, you essentially use this kind of force to create continuous films of molecules on the basal plane of two-dimensional materials. Whereas from the center to the right, you actually use these kind of forces to to anchor isolated molecule on the basal plane of the two-dimensional material. Now, whatever type of interaction you use, the approach can be generalized. That you start with the 2D nanosheets, and then actually you design a molecule. The molecule, for example, can have an anchoring group that is here, this blue triangle, and a red dot that is the new function that is we want to impart to the two-dimensional materials. You can do this kind of functionalization when you have the 2D nanosheet that is dispersed in a liquid. And so in this case, you create this kind of airy disk, and then you can assemble them into this kind of, let's say, foams or porous structures, okay? And so this assembled structure can be used for different types of application, which are actually chosen based on the red dot that you select previously. And so, for example, you can use this for wearable electronics, for multifunctional coatings, or also for sensing. Now, this is what you can obtain using a monodentate molecule. So with one anchoring group, this blue triangle. But actually, you can also use molecules that they have two anchoring groups that are this triangle now in green. And this allows to tether, so to anchor the molecule to connecting two adjacent nanosheets. And then again, you have the red dot, that is the function you want to impart. Of course, this approach here allows you to create much, let's say, more robust and porous structure. You might have a bit of a problem in terms of processability, because indeed you really create a network, a robust network, and so you might lose a bit in terms of processability from liquid because you have precipitation. But still, the porosity can be very high, and also by design you can really create structure that allows, for example, to host ions, and this of course opens the door to all the application in energy storage. Or you can also have, let's say, groups that allows you to, let's say, enable application in photon electrocatalysis or desalination or sensing. Now, we will use both approaches, but actually I will start by, let's say, in a simple manner, by considering the very fundamental building block for electronics, that is a field effect transistor in a bottom contact, bottom gate configuration. And we will see how the molecular approach allows to improve very fundamental physical properties, let's say processes that you have in a field effect transistor. We will see in particular how this can affect the charge transport through the two-dimensional material. And so I will do this by dividing my presentation in two stories. The first one goes from defect engineering to the printed network to dimensional materials. And let's say, so we consider as a process the one of the charge transport. Now, this starts with a very simple consideration, which are two-dimensional material, like all materials, are defective rich. So you can forget about having perfect single crystals. And so you have a number of defects. Here, there are listed some of them. And actually, at this point, one is fair to say that if you're a physicist, you are quite depressed when you have to handle defects, because you don't like defects, you like perfect matter. Whereas if you're a chemist, you love much more defects, because defects are actually reactive sites where you can do a lot of chemistry. And now this activity started in our group in 2017 when Simone Bertolassi joined our group. So Simone came with a very strong know-how in device physics. He did his PhD in PFL with Andras Keys. And so this is a typical example of the hiring that I like to do in my group, that I bring people that they come with the knowledge that we don't have, and this allows to, let's say, combine their knowledge with the knowledge we have established in my group and expand our understanding and expand our approaches to something new. And so now he came, and he had already, as I said, a good knowledge in fabricating molybdenum disulfide field effect transistor. And you have to be reminded, if you take, for example, chemical vapor deposition crystals or Scotch tape ones, every 10 by 10 nanometer, statistically, you have a defect that can be typically a missing sulfur in the lattice of the molybdenum disulfide. Now, this might be not enough. You, as a chemist, you might like to have more. And so how you can create more? There are a number of ways to create more defects on the basal plane of the molybdenum disulfide and other transition metal dichalcogenides. For example, you can irradiate with the ion beam of the X-ray photoelectrospectroscopy, like we did here with the argon beam. You can anneal. You can use electrochemical stimuli. You can use photostimuli like lasers. So there are a number of different types of, let's say, manner to create defects. And depending also on the type of dimensional material you want to play with and how strong the atom in the lattice are bonded. So here we use the argon beam of the XPS. And you can see that actually doing this, you increase the defectiveness within your crystal, which is accompanied by a drastic decrease of the current through a junction, and you can actually, let's say, plot this as an evolution of, as an exponential decrease of the field effect mobility with the increasing number of sulfur defects. And now, so you're creating defects that are scattering center for charges, but actually, these are also reactive sites, as I said, and they actually they can be healed with a thiolated molecule. Now, thiolated molecules with the SH final group are well established, and because of their interaction with the surface of gold. And so, if you open a catalog like the Aldrich catalog, you can find several thousand of these kind of molecules. And so, of course, all these molecules they differ based on their physical and chemical properties. So you can have already a variety of molecules at your disposal that you just buy it and choose it and use to anchor and heal the vacancy that you have in the molybdenum disulfide. And indeed, this is useful as a way to recover to a great extent the electrical characteristics that we generated upon defect formation. But on the other hand, what one is doing is nothing else than grafting a molecular function on the basal plane of the molybdenum disulfide. Now, let me jump from 2017. I mean, we've been using this thoroughly, but I want to jump to a very clear example that was done by Bin An in my group. Bin is an outstanding postdoc that after 6 years in my group now is getting back to China as full professor in Southeast University. And you can see that he has focused on a specific molecule that is this one here, and in particular two isomers of this molecule. Is a molecule that comprises a benzene ring, a thiol unit to anchor the molecule on the basal plane of the molybdenum disulfide, and two fluorine atoms that either are pointing down or are pointing up. So now this is interesting because you can orient the molecular dipole either out of the surface or towards the basal plane of the surface. Now, what does this mean? That orienting dipole in a let's say, controlled manner means that you are able to have a strong end-doping effect when you use the 2.6 derivative, or a strong p-doping effect with the 3,5 derivatives. This is something you can read by Raman, you can read by XPS, and you can read also electrically. For example, here you can see MOS2 is an N-type semiconductor, and you can see by using the 2,6 derivative, we are increasing the electron transport, and by using the 3,5 derivatives, we are decreasing the electron transport. Now, above all, what I also want to stress is that this approach is quite cool because it allows to discriminate isomers. And isomers are, let's say, molecules that have very similar chemical and physical characteristics, and therefore are very, very complicated to be, let's say, detected or discriminated using different types of techniques. For example, they have the same mass, so you cannot use mass. They have very similar optical properties. So that is also complicated. So let's say discriminated isomer is a hot topic in analytical chemistry. Now, I want to stress that this approach of thiol healing is pretty generally applicable. It works also with tungsten diselenide, so you can heal selenium vacancy with a thiol molecule. I'm not going to go into the details of it. You cannot use selenol because selenol are very unstable molecule. And we recently showed also you can use this to heal tellurium vacancy. Okay, so of course, this is very interesting because it broadens the type of physical properties that the molecule, that the two-dimensional materials possess. But let me jump to the idea of using bidentate molecules, so molecules with two anchoring groups. And actually, this is something that started in a collaboration with Jonathan Coleman. So Jonathan works in Dublin, Ireland, and is a pioneer of the liquid phase exfoliation of all the two-dimensional materials. And so actually, I met him in Dresden. And this was in 2019, more or less, 2018. And he had just published a paper in Science in which he creates films of molybdenum disulfide and makes a transistor out of this. These films were actually printed. And actually, the mobility was pretty low. And he explained that his major problem was the fact that he has all these nanosheets in the channel of the transistor, but the charges were not going from one to the next flake in the channel. And so you need to generate percolation pathways for charges to go through the entire film. And so what I thought is that here we could help him with a bit of chemistry. And the idea indeed that molybdenum disulfide nanosheets that you disperse them on a surface, they can be seen like this kind of piece of the puzzle that are disconnected. So you can actually choose the complementary piece of the puzzle that act as a bridge and connect them, creating a network. Now, if you want to see this a bit more from the chemistry perspective, these are the nanosheets that can be molybdenum disulfide, but we also proved this with rhenium disulfide and tungsten disulfide. And you can use a very simple molecule that is benzene dithiol with the two thiol units that are in the para position. So this is a conjugated semiconducting molecule, and that can be used to covalently interconnect the adjacent flakes. And so it has actually two effects on the same time. The first one is to yield sulfur vacancies, and the second one is covalently bridging adjacent flakes. Now, how do we prepare this kind of network? That's pretty simple. So we get the ink in ethanol coming from Jonathan, and then we buy some, interdigitated electrode supported on silicon dioxide, and then we drop cast our ink. We create this kind of film, and I use the word film when the flakes are disconnected. Then we put this in a controlled nitrogen controlled atmosphere, and then we apply a drop of our benzene dithiol. Now, this has to be done actually in the dark and inside the glow box, which allows to avoid photo-oxidation. Now, doing this, we create the one that I call network, that is where the nanosheets are linked between them. And so let's say this is a picture to show you what we have been doing. Essentially, we have been connecting adjacent nanosheets. I skip the whole characterization part, demonstrating this network formation really took place. This has been, let's say, monitored by Raman spectroscopy, by XPS in particular. And I want to jump directly on the how we can use this to improve the electrical characteristics of our material, of our film. And so we use liquid gated transistor because in this case we can use a dielectric liquid that penetrates the free volume of the semiconducting film. And so the bottom line is that upon network formation compared to the film, we have an increase of tenfold of the field effect mobility, tenfold of ion-off ratio, and we have no doping effect, at least that we perceive, because threshold voltage remain unaltered. Now, we have been demonstrating this also in a number of studies, included the one of our chairman, Professor Bon, in which he showed very nicely by TRS spectroscopy that we have, upon network formation, we don't have major changes in the intraflake transport. Namely, this allowed us to rule out that there was a major effect. The major effect was coming from interflake type of transport. Now, another example of this benzene dithiol is something that we have reported recently, again by Bin An, which was addressing another type of defect that you have commonly in two-dimensional materials, and these are line defects. Line defect that you have in particular in Scotch tape or CVD type of crystals. And here we focus our attention on tungsten disulfide, just to show you again that this approach is broadly applicable to different types of disulfide, diselenide, and ditelluride molecule, to the materials. So the idea was pretty simple, that CVD crystals, they can have this kind of line defect, and we decided to use the benzene dithiol in order to weld this defect, so to connect the two adjacent crystals. You, of course, doing that, you increase the content of sulfur versus tungsten that you have within the film. And now the effect can be both on the optical and on the electrical characteristics. You can see here that as soon as we heal the line defect, we have an increase of 3.5-fold of the photoluminescence in our film. This and the grain boundary is not observed anymore upon this kind of healing formation with the benzene dithiol. And likewise, you can also observe that we have a major increase of 200-fold of the field effect mobility, and the increase of 10 to the power 5-fold of the ion-off ratio. So what is quite striking is this example here, that you have the interdigitated electrodes, and you have electrode 1, 2, and 3. And we have a line difference between 1 and 2, and we have no line difference between 2 and 3. And therefore, upon healing, we can see that we can have a major increase when we measure the current passing between the electrode 1 and 2, that you can see it here from this to this curve here. Whereas when you are wiring up electrodes 2 and 3, upon the healing, you have a much more modest increase in the current through the junction. Okay, this kind of treatment is lasting quite a long time, so it's quite robust. Now, what's next? I think that actually somehow this approach opened the door to the transition from 2D nanosheets to 3D network of these, and here you can really use your creativity. You can use your creativity using different type of two-dimensional materials and using different type of bridges. Now, these are just the beautiful bridges you can find around the world, but here the bridge from the chemistry perspective, it can be functional. Namely, for example, you, instead of a benzene ring in between the two toluene, you can have a receptor of a given analyte. And so that allows you to do a lot of study in the direction of sensing with the high selectivity coming from the chosen receptor. They interact at the supramolecular level with the analyte of choice. I have no time to go into that. We already published a couple of papers in this direction. I would like to pass to the story number 2. And the story number 2 actually is about taking functional complexity in hybrid organic-inorganic heterostructure. And we go all the way down to emulating also brain logic operation, which I think is a very interesting topic nowadays in electronics. So again, we start from two-dimensional materials, is on charge transport characteristic, and its high sensitivity to the environmental changes. And but environmental changes means also an environment you can artificially construct upon, let's say, interfacing with molecules. So let's say, before starting this kind of activity, we have, let's say, written down a kind of ideas that we had in mind in this progress report together with Marco and Emanuele. So that was done in 2016, 2017. And now, but the idea overall is pretty simple. And I like sometimes to make correlation with things that are pretty distant from science. That is, for example, food. Now, you can consider to taste a hamburger, and you can consider the way of chewing a slice of cheese. They have a given taste, but the sum of them actually does not have a taste that is just simply the sum of the two tastes. So that is, let's say, is a concept of an hybrid. That hybrid has the properties that goes beyond the sum of those of the individual component. And of course, in food, but also in material science, you can construct more and more sophisticated type of structure or assemblies, which have more and more interesting type of properties. And so you can just have to play by overlapping two-dimensional materials one on the top of each other, for example. And that is what has been done by the physics community by fabricating van der Waals 2D-based van der Waals heterostructure. And a huge number of papers that are showing the outstanding new properties that you can emerge out of this kind of interfacing. For example, you can see here this kind of nice noir pattern. You can read, for example, this kind of, let's say, perspective article that was written by Andre Geim more than 10 years ago. Now, the open question that I like to bring up is how you can dope two-dimensional material with molecule. And let's look into the mechanism of doping. And also, it would help if we have a kind of doping that can be reversible, because we can turn on and off, so we can gate it. And this allows us to have a better control over the effect. And so there are two main mechanisms of doping two-dimensional material with molecule. So the first one is a molecular dipole-induced shift in the work function. So this can be obtained when you have a molecule with a high dipole moment, and actually you place this molecule on the basal plane of the surface of the two-dimensional materials. And so it's the electric field that is emanated by the dipole that acts as a local gate and shift the work function, and thus induce a doping of the two-dimensional materials. Now, this effect can be maximized the more you are able to align individual dipoles. And so that is actually will be strictly connected to being able to assemble molecule in a controlled fashion on the basal plane of the surface two-dimensional materials. The second one is based on charge transfer, and we'll go through this in a few minutes. So let's start with the first one. And indeed, playing with dipole, playing with assembly of molecule is very important to maximize this effect. And so you can actually play LEGO. Playing LEGO means that you have the two-dimensional material that is your base, your playground, and then you have your molecular brick, and you have to find let's say, supramolecular approaches in order to align your bricks and to make them, let's say, forming a kind of superlattice on the top of the two-dimensional material. Now, how you can do that? That is pretty simple, actually. Let's start considering two-dimensional material being graphene, but can also be easily a transitional metal dichalcogenial like molybdenum disulfide. And the most simple molecule that you have in this world that are alkanes. Alkanes, actually, they love the basal plane of graphene, which is a very same basal plane of graphite. And this was demonstrated about 40 years ago by my former PhD advisor, Jürgen Rabe, that you can assemble alkanes into a crystalline lamella structure on the basal plane of graphite, and you observe this by scanning tunneling microscopy. Why? It's because actually graphite, they love to physisorb along the zigzag axis of the basal plane of graphite, which is a very, very same basal plane of graphene. So you obtain what? You obtain this kind of crystalline lamella structure you can map with scanning tunneling microscopy. Likewise, you can have the same type of assembly, also molybdenum disulfide and other TMDs. So now, from a chemistry point of view, alkanes are simple molecules, as I said. By what you can do, you can add a function, for example, at the end, as an end group. And this allows to, let's say, decorate the basal plane of two-dimensional material with a specific function, which is placed on the surface with an atomic precision, because it's dictated by the assembly of the alkanes. Now, so what we are doing is nothing else than a precise function decoration. Now, why do we do that? Why do we want to impart new function to the two-dimensional materials? Actually, it's because I made a very simple analysis that most of the devices that we are using are monofunctional. For example, a field effect transistor can be turned on and off by applying a voltage to the gate electrode. This is like having a remote control with one button, but my idea would be using chemical tricks to add more and more buttons to the remote control to make them multi-responsive and multifunctional. And so how do we do that? We start, first of all, with photochromic molecule, which are small organic molecules that are able to undergo efficient and reversible photochemical isomerization between different states. And these states, they exhibit different properties. And so, for example, these are the three most well-known type of photochromic molecules. And the most famous one is the isobenzene, that you can trigger the isomerization from the more extended transform to the more compact cis form using UV light. And then you have the reversibility that comes with visible light illumination or with thermally. The two states, they have a pretty different conformation, okay? Now, on the extreme right, you have the spiropyran. There actually you can switch from the neutral spiro to the zweiterionic merosanine. With UV light, you can go back with visible light and thermally. The two states, they have quite a different dipole moment. So if you want to have system where you change the dipole moment, this is the one to be used. Now, in these two examples I mentioned, the state on the right are metastable, so they're not thermodynamically stable. Instead, the big difference can be found in diarylitin. Diarylitin, that is here in the center, you can switch from the open to the closed state with UV light. You can go back with visible light from the closed to the open state. The two states are thermodynamically stable, and this is very interesting for digital electronics. And on top of this, the two states, they have different energy level of the frontier orbital. And you can see here, for example, the LOMO level, of the HOMO level. So let's get it started and try to use this in a digital fashion. So we start with the spiropyran because we want to use the idea of aligning dipoles. And as I said, dipoles change. The major one you can find with spiropyran. This was the work of Marco, Sara, and Emanuele, a physicist, a chemist, and engineer. So that's the kind of subgroup that I create in my laboratory because it allows really to use material science to its best, to its, let's say, interdisciplinary type of approach. Sara brought the photochemistry, Marco brought the device physics, and Emanuele device engineering. And so this spiropyran has a characteristic as this R group that is a very long alkyl chain that is long 18 carbon atom, linear one, so octyl chain. and this forces the molecule to assemble into this lamella structure, and therefore we are positioning with an atomic precision the spiral unit on the basal plane of the graphene, and later also in the molybdenum disulfide, making dry films by spin coating that can be isomerized to the Mero form with UV light illumination. Are we certain about that? Well, we are certain because we can do UVV's absorption of a monolayer of our spiral supported on a CVD graphene that is absorbed on quartz. And we can map this with UVV's absorption spectroscopy. We can map this also with the X-ray photoelectron spectroscopy. Why? Well, we focus on the N1S peak. And as you can notice here in the spiral is the nitrogen is in its neutral form, and therefore upon irradiation with UV light, we create a Mero where the nitrogen is positively charged, which is accompanied by an emergence of an appearance of this blue peak that can be ascribed to the positively charged nitrogen, which vanishes to a great extent upon visible light illumination when we go back to the Mero, to the spiral form in which the nitrogen is neutral. Now, we can monitor this kind of two states by scanning tunneling microscopy. I don't want to enter inside detail. This is just to say that we have the formation of lamella structure on graphene, and the packing is different in the two cases of spiral and Mero, but it's reversible. And then now we fabricated devices, a backgated field effect transistor, and you can see here the idea is that we have in black the clean device, so it's pure graphene. Upon physisorption of the monolayer of spiral, we have a very small end-doping effect. Then upon UV light illumination, you can see that this kind of end-doping becomes major. We obtain this kind of blue curve, which is totally reversible upon visible light illumination. So we have a reversible doping effect that can be quantified. And so with a carrier concentration change that is 4.4 10 to the power 12, which is a pretty major. I don't want to emphasize detail, but the very same effect can be observed also on molybdenum disulfide devices instead of the graphene one. Now, let me now move to the second type of physical process that can be used to reversibly dope the two-dimensional materials. That is charge transfer. And this is all about the energy level alignment that determines the doping by favoring the transfer of electrons from the two-dimensional material to the molecule or vice versa. So this was the work that was done by Aixin Q in her PhD thesis in my group under the supervision of Zhaoyang Liu. They are both back in China now. She is in Shanghai Jiao Tong University. Zhaoyang is in Jilin University. Now, here we focus on tungsten diselenide, and we chose this because it's unique. Depending on the thickness, it can act either as an electron transporting material or as an amipolar material. So in the first example I will show you, we treated the tungsten diselenide in a thickness that was electron transport material. Later we will see how it can also be used as amipolar. Now, and here we combine this with the diaryletin. Diaryletin has the peculiarity of having high fatigue resistance, thermal bistability, and phototunable energy levels. And together with Stefan Hecht in Berlin, that is our synthetic partner, in such that his LUMO level was, let's say, falling out of the band gap for the open state and in the band gap of the tungsten diselenide for the closed state. So now, let me explain you what it means to have a dopant whose level falls in the band gap of a semiconductor. This means that the dopant will act as a trap for the charges of the semiconductor, whereas when the dopant level falls out of the band gap of the semiconductor, the interaction are pure electrostatic. So essentially, we can dope and undope, or trap and untrap our 2D semiconductor. Now, how did we fabricate the device? This was pretty simple. We scotch tape tungsten diselenide. We transferred this to the silicon dioxide surface. Then we fabricated a backgated device with a laser writer and depositing gold contacts. We vacuum anneal at 100 degrees to get rid of all the residues from this kind of patterning. And then at this point, we physisorb by spin coating a 3 to 4 nanometer layer of diaryletin on the top of the tungsten selenide that is already in the channel of the device. Then we characterize electrically our device in the dark and under illumination at different wavelengths under, let's say, within the glove box to be in absence of oxygen and water. Now, we start from an unoptimized device of this bare tungsten diselenide, mobility of 16 centimeters squared per volt per second. We physisorb the dialyte in the open state, which is actually the one that is not trapping. And so we have a reduction of the mobility that is quite minor, is about 20%. Then at this point, we irradiate in situ with UV light. So we close the diaryletin, and we actually have a mobility decrease of 50%. And now at this point, we can, because it acts as a trap, the diaryletins, then we can irradiate with visible light to reopen the diaryletin, and you can observe that we recuperate fully our initial mobility of 13 centimeters squared per volt per second, and the threshold voltage is back to the initial value, so we are undoping our device. Now, as I mentioned, the one characteristic of tungsten diselenide that, depending on the thickness, can also behave as a ambipolar material. And so that is what we have done. And now in this case, actually you have to think of doing something similar, but considering that you can play on the same time, not only on the electron transport, but also on hole transport. And so this means that you have to think not only in terms of the conduction band and trapping and untrapping the electron transport, which is what we have done in the previous example. So we can use the very same molecule for this, but also we can have a second molecule that is interfaced on the same time to the tungsten diselenide, which is another derivative of the diaryletin that by design is homo-level, falls in the band gap of the tungsten selenide when it is closed, and in this case, when it is open, it falls out of the band gap. And so we are trapping and untrapping the whole conduction. And this kind of energetic level consideration has to be done by considering, in this case, the position of the valence band of the tungsten diselenide. And so the idea is pretty simple, that we physisorb a blend of these two molecules on the basal plane of the tungsten diselenide in our device. And doing that, what you can see is that we can start from the mobility of 30, all mobility of 35, and the electromobility of 43. Upon physisorption of the tungsten selenide in the open state, we have more or less the same mobility, a slightly increased electromobility, which is quite remarkable. And then what happens is, upon UV light illumination, we observe that we have a decrease of 96%. So going down to 1.2 centimeters squared per volt per second of the whole mobility, and decrease of 40% of the electromobility, which is totally recuperated upon visible light illumination. And so you can see here. Now, this is quite interesting because it's important for, let's say, consideration in the context of ambipolarity and having more sophisticated devices. Now, that are, let's say, try to imitate CMOS type of device. Another consideration is the fact that two-dimensional material structure is very well defined, and actually you have a bottom surface and a top surface that can be asymmetrically functionalized. And so using a kind of Janus approach to, let's say, to boost the functional complexity, and by exposing essentially the two faces to different local environment. And so what are the local environments we can molecularly fabricate? Well, these are, again, starting from tungsten diselenide in a transistor, we can expose the bottom surface to a photochromic layer. And here we already have been playing quite enough with this. And the top surface is the ferroelectric material. As this allows to have a dual response to the optical and to the electrical stimuli. Now, photochromic we already discussed, and we will go back to this. For what concerned the ferroelectric material, we thought that there was no need to invent something totally different. We took let's say, the very interesting concepts that were brought in the community by Dago Deleuve, that actually was the Max Planck in Mainz together with Paul Blum, and Professor Azadi, that is now in UK, by introducing the use of this PVDF therapy, that is a polymer that you can see that highly fluorinated, and upon applying an electric field, you can swap the orientation of this fluorine atom, either pointing up or pointing down. They are pointing down, they are pointing towards the interface with tungsten diselenide. And so they are creating dipole at the interface. And so that actually can be used in order to accumulate or deplete the state of the charges in the device. So that was more or less our device architecture. Let me show you a bit more, let's say, clearly in the next slides. I don't think I need to introduce much the ferroelectricity. When you apply an electric field with a coercive field, you start aligning dipole. They can be totally aligned or partially aligned. And now our device actually consists of indeed a stack of vertical stack with silicon dioxide aerylithium layer, tungsten diselenide, the layer of our ferroelectric polymer, and then a gold electrode. Now we are radiating device from the very top, and I was not certain that with photons I could reach let's say the diorating layer. The reason is because the ferroelectric material is pretty thick, is about 600 nanometers thick. But actually, to my happiness and surprise, this was not an issue. And so we tested the optical switchability, say the possibility of using light at different wavelengths to change the electrical characteristic of the device. You can see here we can change about 60% the current through a junction by irradiation with UV and visible light. So UV, we close the diorating, and visible, we reopen the diorating. And this allows to a very reversible modulation of the current through the junction. Now, we had to learn how to use with the ferroelectric material. And actually, we noticed that upon applying a plus 60 volt, we are orienting all the dipole pointing towards the surface of the tungsten diselenide. This is the highest current possible. And then upon applying minus 60 volt, we swap the dipole orientation, they're all pointing up. And this we have a change of 68% of the current through a junction, and which is also totally reversible. So these are two types of, let's say, stimuli that are non-volatile. Now, let me also show you how you can use the two stimuli independently, but on the same device together. So with a device in which all the dipole are pointing down and the diorating are in the open state. So this is the highest current that we can observe in our device. Then what happens, we illuminate with UV light, we close the diorating, we create optically some traps, and we lower the current through the junction. Still, all the dipole are pointing down. Then we apply minus 60 volt, we swap the dipole orientation, which now are pointing out of the surface. This is the lowest current that we can achieve. We illuminate with visible light, so we get rid of the traps of the diorating, and then we apply plus 60 volt, and we swap the dipole. Now pointing down. So we go to the initial highest current position. And so that is to show you that you can use the two stimuli independently. Now, why can this be interesting? This can be interesting for memory application, given also the two, let's say, the two types of stimuli are non-volatile. And so, for example, if you use a fast laser, you can actually each pulse of a low power UV laser, you can trigger the isomerization of a finite number of diorating that you have interface with the tungsten diselenide, and you can stepwise lower the current to the junction. So you can see here that each pulse you have decreasing current. Now, this was done in my laboratory. We are not equipped with very fast laser, so we could actually draw 84 different distinct levels. When we did this in Nova Gorica with San Colita, they have an ultra fast laser of 3 nanoseconds inside the glow box. And this we can actually increase from 84 to 256 levels. Now, also, as I mentioned, the application of a voltage allows you to have a total or also a partial orientation of the dipole. And this has been used in order to observe 9 different types of level in which that can be controlled by electrical stimuli. And so if you sum up this kind of two type of stimuli, you can actually have 9 level states that derive from the ferroelectric material, 84 from the photo controlled one. And so that allows you to reach essentially to fabricate a 9-bit memories, which can be increased up to 11-bit memories if you use a fast laser. Now, so what is our approach? Our approach is actually the one of going beyond Moore, in a more than Moore approach that towards functional diversification, in which we get a huge inspiration coming from nature that works by putting function to interface, and this is what we do. And in a device like a field effect transistor, you need to identify where are the interfaces and how you can put a function in a given interface, not in another. So, for example, how you can put a specific molecular function in 1 and not in 2 and not in 5. And so what function can you use? I showed you that you can use stimuli responsive systems. They respond to light, they respond to electrical stimuli, but there are a number of other types of stimuli responsive systems. You can think of, for example, those that respond to magnetic, to electrochemical, to pH, to enzyme, to mechanical stimuli, and so on and so forth. And so that is our approach that we use to boost, in order to boost functional complexity. And we use this also to emulate neuromorphic logic. And this is the last example I like to show. That is actually the idea of trying to emulate the way our brain is storing information. Our brain can store information for a short period, for a long period, and also, in some rare cases, also permanent period, so permanent memory. And the first two cases are done by ion migration. The last case requires protein synthesis. Now, the way we are doing in my laboratory to emulate this kind of memorization is actually by using, they say, the whole arsenal of molecular switches that have been developed by the community of supramolecular chemists in the last 50 years. And actually, in all these switches that can respond to light, to redox, to electrical stimuli, and so on and so forth, we know them very well, their kinetic and thermodynamic. We know how stable one state is with respect to the other. And this allows us to control how long is the storage of an information to emulate the short and long-term plasticity, or also the permanent memory, because this can be done easily with non-volatile type of switching, like the one of the ferroelectric material I showed you so far. So let me show you super briefly the last example I have to share with you. There was a work done by Ye Wang. Ye did her PhD with me, and after a postdoc in Cambridge, now she's professor in TU Eindhoven. And the idea was, again, the Janus type of approach to interfacing the two-dimensional materials in an asymmetric fashion with two different environments. And two-dimensional material that was chosen was molybdenum disulfide. We had a bottom gold electrode that was covered by a chemisorption layer of azobenzene that can undergo isomerization from the more extended to the more compact form, so from trans to cis. And the top of the molybdenum disulfide was interfaced with ionic gel, in which we dispersed ferrocene molecules. Ferrocene, of course, are they say, subjected to electrochemical stimuli. They can be oxidized. And actually, what Ye has been able to demonstrate is that depending on the voltage we apply to our dielectric tool, that is our ionic gel, we can actually, for low voltage, below 2 volts, we can each pass can trigger a short-term plasticity, potentiation. So, namely, as soon as the pulse is released, our system goes back to the initial current. Whereas higher voltages, above 2 volts, each pass trigger the field distortion at the interface with molybdenum disulfide of more and more ferrocenium molecule. And this actually is a much longer lifetime and can be used to emulate long-term plasticity, which can be finely tuned upon changing the state of the azobenzene. So let me just show you this. Well, this is just a CV spectra of the oxidation of ferrocenium to ferrocenium. And you can see here on the total right that you have 2 peaks in our CV case. One is due to the oxidation, and the second one is due to the absorption of the molecule on the surface that occurs at higher voltages. And actually, we can change the state of the azobenzene and have this kind of tunnel ruled, let's say, injection in this junction between gold and our semiconductor, depending on the state of the barrier introduced by the thickness of our layer of the azobenzene. And then actually what we're going to use, and here is just the cartoon, is that if we use the low voltages, we have below 2 volts, we have each pass, we trigger the oxidation of the ferrocene to ferrocenium, and then when the pass is off, it goes back. Instead, higher voltages is such that each pass, we have the absorption of this ferrocene at the very interface. You can see 1, 2, and 3 molecules that are absorbed at the interface with the fine-tuning that comes from the azobenzene states. And you can see here the result that low voltage up to 2 volts, you can see we have a very short lifetime of our new state that is created. Higher voltage, we have much higher lifetime, which this is a potentiation process, and we have depression, so we can erase our memory by applying a -5 volts, so change the polarity with a much higher voltage. Now, if you're interested in how we continue and we see this kind of interaction between molecules and two-dimensional materials beyond Muir and beyond CMOS application, you can read this kind of review article. It was written by Yuda Zhao, former postdoc in my lab now in Zhejiang University. And I think the take-home message of this is that they say the chemistry offers a lot of opportunity when interfaced with dimensional materials. And actually, I showed you they mostly result in electronic, but this is also, it can be used to impart new properties for sensing, catalysis, and similar response in mechanical and electrical characteristics. So we can create, let's say, emulate sophisticated function. You can use this for health monitoring. And overall, I think you can also come up with some new disruptive technology, which I believe the responsibility of the scientist is the one of trying to address some of the big challenges that our society has to face or is facing, and by providing very small answer using our material science approaches. So all of this has been possible thanks to, let's say, an extensive network of collaboration. Actually, our activity is pretty narrow, and we learn and we benefit out of collaboration with a number of colleagues that with coming or operating more in the, let's say, field of two-dimensional materials. Here are listed some of them: Xilian Feng, Klaus Mullen, Jonathan Coleman, our chairman, Maurizio Prato, Francesco Bonacorso, Andrea Ferrari, and so forth. But also from the molecular side, we have very strong interaction with different colleagues. In some cases, providing some new chemical systems, some other cases, let's see, looking at properties that we are not able to address in my group. Finally, the people that made this happen are my collaborators, my younger collaborators. Those that are presently in the group are depicted in this image. Again, to do this kind of science, you need to have interdisciplinary group. You need to have engineers, because those are able to fabricate better devices, but you need chemists because they're able to play with the chemistry of the system. And then also, finally, I'd like to acknowledge our sponsor, that in particular, European Union is investing quite a lot of money in science, and they have to do more and more, because that's the way to construct a better future for a new generation to come. And thank you very much for your attention.
Thank you so much, Professor Samary, for the fascinating presentation. Now we will open the floor to questions. If you have any question, please type into the Zoom chat or feel free to open your microphone, and we will call on you to answer your question directly.
Maybe I can start with a question, Paolo.
Sure.
Many thanks for this. Between dipolar doping and charge transfer doping. And you showed that with dipolar doping, specifically in graphene, you could reach very high charge doping levels. And I wonder if you have such a sort of charge transfer state on the surface of graphene, whether you can really talk about dipolar doping versus charge transfer doping, whether there's not also charge transfer involved in when you have such a charge separated state. Do you have any thoughts about that?
Yeah, that I think is a very good point, actually, because in particular, when you deal with semi-metal like graphene, I think that's indeed is that the question is how to address this question. I mean, how can we experimentally monitor these two effects? Maybe some of your tools, I guess, because I mean, what we would love to have is to be able to discern the two effects, right?
Yeah.
That I mean, not easy. I don't think it's going to be very easy. We need probably to design the right system.
Yeah, and I think there is a kind of a gray zone, right? Between so there's this whole debate about charging of hydrophobic surfaces, and there's theories that claim that there is some charge transfer. So it's not a whole electron that's being transferred between
Yes.
the water and the hydrophobic interface, but there's some partial charge that's being transferred. And that, of course,
Absolutely.
yeah, has to do with the dipole also.
Yeah, that's a very good point. It's absolutely a very good point.
So maybe I can just continue because I have another question, if that's okay with you. So
Sure.
you in your experiment you talk a lot about solvents, and you also use dielectric liquids in your FETs, and of course, and then you use molecules to well, chemisorption to change the properties of your 2D materials. But the solvent, presumably, at least some of your solvents, and it's certainly they're dipolar, will also affect the properties. And I understand that, after you make the device, the solvent is gone. But could you think of a way to make use of solvent properties, not just for the assembly, but also in defining the properties of your materials? A bit like, like the equivalent of defect engineering, but then solvent engineering.
Yeah, absolutely. That's a very good point. We had two papers, I think were more or less 2017, 2019, in which we indeed focus our attention on solvent. And this was on different types of 2D semiconductors. And the bottom line, and we have analyzed the interfacing, the washing of different types of two-dimensional materials with a number of solvents. That was also, some of them you might have wondered whether they were innocent. None of them is innocent. Okay,
right? So that's my feeling. So right.
That's the point. I mean, so let's say if I had to jump to the conclusion is, as if you want to make sure that you don't have a solvent effect, the best would be to find a way to deposit molecule from a vacuum phase. Okay, so
right.
that
right.
You get rid of, let's say, potential interference. Otherwise, you have to do all the blank experiments. I mean, really, we tested so many of them. Even more apolar one, like, we consider, of course, the chlorinated one, because those are mandatory. We need to use them, when we deal with let's say, liquid phase swim. But we try the most common ones. So DMF, we try NMP, we try benzene, we try toluene, we tried, I think there was a huge library, and we had also calculation coming from Mons, from David Beljon, in which it showed essentially we were looking at Tryon's effect, we were looking at the mobility in the device, and the bottom line is blank experiments are required when you play with solvent, because you need to subtract the effect of the solvent, or play with the vacuum sublimation.
Yeah. And so you mentioned our mutual collaborator, Xinliang Feng. I'm actually just in Dresden, and I had a coffee with him yesterday.
Okay.
And we discussed it a little bit. And of course, you take existing 2D materials, you do very clever defect engineering to functionalize the materials. He, of course, has a different approach, I would say a complementary approach, where he makes 2D materials sort of bottom up. They're organic, so they don't all have the same perhaps robustness that your systems have. But it allows for very sort of subtle tuning of properties, right? And he can incorporate functional groups in
Absolutely.
his 2D materials. How do you see that? Is that is it just complementary? Is it competitive technology? Is it?
Well, we do also that. We do also that, and I think they are complementary. For example, we do interface MOFs and COFs with two-dimensional materials, okay, to make superlattices. So there we had a couple of papers in that direction. So this approach is amazing because somehow you can really bottom-up tune the functionality. And so for a number of properties, that's the best tool. Of course, it's more complicated from his side to make perfect, large, and robust, let's say, nanosheets, which is, so it's a big challenge also from the processing point of view. But I think the two things are highly complementary, and they must be used in, let's say, in a concerted manner, for sure.
Yeah. All right.
Hi, Paulo. Nice to meet you. I'm Tong
Hi.
Zhu from Beijing Institute of Technology, and thank you for your really impressive talk. In your earlier slides, you did mention about tuning the interaction between organic molecules and the 2D material, like from van der Waals interaction to covalent. So actually, we did some like ultra-fast spectroscopy work on WS2 and tetrasin, like those small molecule heterostructures, and characterize the charge transfer time between the two materials about like within 1 picosecond. So I'm wondering, like, do you have like any idea how fast it could be for those covalent interaction if you link the molecule onto the 2D material? Like how fast would it be?
Yeah, that is something that we still have to study. That's something we still there is. Yeah, we've been focusing mostly on the electronic part, and we have a look very much into how this kind of process can be, how fast this process can be. Sorry.
Yeah,
but that's I think quite interesting because indeed, I mean, the idea is we are creating now networks of two-dimensional materials. So what are the properties of these networks? Okay. I think this really, it opens the door to a number of very fundamental type of studies.
Okay, yeah, thank you.
Thank you for the inspiring question. Oh, sorry.
Hi, Paulo. Thanks for your impressive talk.
Hi, Shane.
Hey, actually, I have a question. You mentioned about use the tile chemistry to repair the sulfur vacancies. And do you see the possibility to quantify the defect density before and after this vacancy healing?
Yeah, that can be quantified by XPS. But also we recently we have been using in direct manner in collaboration with the group of Sarah Bals in Antwerp by using a high resolution TM, okay, aberrated corrected. Essentially, if you start from a defective rich type of lattice, if you look at the unit cell size, you will have a huge error bar, which will decrease, will become much more narrow. So the standard deviation of the error of the lattice will become much more narrow once you have been healing the defects. Okay, so just by looking at the standard deviation of the axis of your unit cell is an indirect manner to see the healing process that took place. So that's one way, and you can also count the missing sulfur atom, for example, in molybdenum disulfide lattice from electron microscopy image. This is what they do in Antwerp. But as I said, you can do this by XPS.
Okay, thank you.
Hello, Paulo.
Hi, Ray.
Hi. So
nice to see you.
Thank you for addressing us this nice talk. So I have a question. In the framework of supramolecular interaction, is it possible to find a way strong enough to dope 2D materials like MOS2 into a P-type semiconductor? So I noticed that the threshold voltage can be easily adjusted using the, very weak supramolecular interactions. So is it possible to develop some method to combine the advantages of supramolecular interactions and a very strong doping or some mechanism to significantly affect the band energy of 2D materials? That is my question.
I think, yeah, no, that's a good question, but I think you start from a complicated case. I mean, Of course, molecular approach can be used to boost one channel of conduction more than the other. But you take an extreme case, the one of the molybdenum disulfide that is a strong N-type. I'm not sure that this is doable, but I would start with something a bit more in between. Like, you take it an ambipolar, like tungsten diselenide, and you boost the P-type channel with respect to the N-type channel using the molecular approach. That I think is much more doable. I would not start from the complicated case that you are suggesting. I don't think it's going to be so
easy. Because maybe MOS2 is too.
It's too strong in type.
It's too strong in type. Yes, it's true.
Yeah.
But now I think the people who work on MOS2, the most concerning point is that how logic onto one substrate with very large crystal studio materials, something like that.
Well, there is also the other problem that frequently MOS2, when you get in you can exist in different phases, and you would love to have a pure 2H phase, that's a pure semiconductor phase, and this is very complicated to get. Okay, in particular, I'm not talking about the CVD, but I'm talking about the liquid phase. And so to get a pure 2H, that is challenging, and that's one of the biggest challenges that you can have, because you don't want to have traces of the metallic one, okay, which is actually the case in most of the compounds that are around.
Yeah, okay, thank you.
Hello.
Hi, Lily.
Hello, Paulo. Hello, Lei. It's really good to see you both here.
Absolutely.
And it's a great pleasure to have another tour of the molecular approach to the 2D material. And it's a good chance, I think, to have an overview of all the work in your group. I just realized there is I have a question raising that. When you introduce the first part, you use the anchor group small molecules to the 2D materials, right? There is a tail group of, I think most of the case use a tail group, right?
Yes.
But when we turn to the photochromic molecules, actually there is no anchor group there, right? To the photochromic molecules, whether the mechanism will change to.
Yeah. So no, it's not totally true. I haven't presented this, but we had with Yuda, we attached, for example, ferrocene to the semiconductor by using a thiol unit. We have some results on dilating with the thiol groups, and we are working on finalizing that kind of study. But we have also thiolated photochromic molecule connecting a decent flake. That is something still unpublished, but we are on it.
Yeah,
so it's
great to hear that. I'm looking forward to see why this entry group of photochromic molecule will change the tunabilities.
No,
Great.
it's something we are working since 3 years essentially, and we are getting further. So
Okay, great.
thanks.
Yeah. Is there any questions? Okay, it seems there are no more questions at the moment. Thank you again, Professor Summary, for your insightful presentation and thoughtful answers. We also appreciate everyone's participation and the great questions today. We hope this session has been informative and inspiring. Thank you all for your attendance, and we look forward to seeing you at our future events. Please feel free to reach out if you have any questions or would like to learn more about our journal. We look forward to your continued attention for smart devices. Have a great day.
Thank you very, very much to all of you. Thanks for being there. It was great to see you all.
Thank you
See you
very
soon.
much.
Likewise. Thank you. Bye-bye.